In this lesson, we're going to take a look at linear functions and learn what it means to be a linear or nonlinear, and how we can decide if a function is linear. Well, so first we got to decide what the word linear means. Linear. So take a look and say, what word do you see in there? Well, you might say, I see ear. Well, this has nothing to do with an ear. Now, what other words do we see in the word linear? Well, the word line is right there at the beginning. Okay, it's a linear function. It has a line. So when a graph makes a line, that makes it a linear function. Okay, so let's look at our exploration here. So what we're going to do is we're going to take in this first two, A and B, we're going to use this graph, right, this rectangle right here. Okay, we want to complete each of these tables for this of similar figures. Okay, and so we're going to use the rectangle here for the A and B, and we're going to graph the data that we end up getting in this graph. Okay, so and then we want to see if it's a linear relationship or not. So first we're going to talk about the perimeter, and then we're going to find the area. Well, we know perimeter of a rectangle is just to find the length of all the sides, or we can say perimeter is 2 times the length plus 2 times the width, and we know the area is length times width. All right, so for example, if x is 1, well, that would mean that this is 1 and this is 2 times 1, which is 2. And so our perimeter there would be 2 plus 1 plus 1. Well, that would be 6. So if x is 1, then the perimeter is 6. Well, that's if x is 1, but what if x is not 1? And if x is 2, or if x is 3, 4, and 5. Figure out what those are and then graph them. And then do the same thing and find the area, or you might even fill in the table at the same time. You decide. So if x is 1, we have 1 by 2, because it's 2 times 1. Okay, and you can find the area would be 1 times 2, which is obviously 2 square units. Now, these are square units. These are regular units, linear units. But anyways, graph them, and we'll compare them there. Okay. And we want to decide whether it's linear or not. So just label it as linear or not linear. And then come down here and think about a circle. Okay? A circle with a radius r. So if we have a circle like this, and our radius going through the middle here is r, well, we know the circumference of a circle. What's that formula? Well, it's 2 times pi times the radius, or pi times diameter. What's the area of a circle? Well, that's pi r squared. Okay, so again, for this one, take 1, put it into r, figure out the circumference. Okay, and put them all there, okay? You might want to go ahead, and on this one, you can multiply it out. Okay, so get a calculator out, that's fine, and multiply 2 times pi times r, get the decimal value, and just write the decimal value down here to the nearest 1 decimal place is fine. Okay, something like 6.2, so on and so forth. Okay, and write these down there, and then graph it and see what you get. After you do that, come take a look and continue this video. So pause the video, try those out, and come on back. All right, so let's take a look at what we should have got. For our area, we should have gotten 6, 12, 18, 24, and 30. And we plot our points, it looks like this. For part B, we get 2, 18, 32, and 50 for our areas. And when we plot those points, we get this: 1, 2, 2, 8, 3, 18, 4, 32, 5, 50. Notice now we're just approximating where this is. I know that this is 20 right here. This line is 15 high, 20 and 15. So 17.5 is right in the middle. 18 would be a little bit above. Okay, so it's an approximation there, so that's good enough. Now the question on these two is which one's linear, if any of them. And so if we draw a line, if we try to draw a line, well, that's not a very good line. Okay, so if we kind of connect these points, we see that that one's a pretty straight line. It would go on in that pattern. So this one is linear. That is a linear pattern. Okay, this guy right here, if we kind of connect these points, it's kind of got a curve to it. I missed that point, but we can see these are not aligned. Okay, does not line up. So these are non-linear. So the first one's linear, second one's not linear. Let's try the next two. Our circumference problem, we see that yes, we have a linear function. We go 6.3, 12.6, 18.8, 25.1, 31.4 if we're rounding to the first decimal place. And yeah, that looks pretty much linear. We got a line that goes right through it there. Something like that. And this would be linear. And for our area graph, we got 3.1, 12.6, 28.3, 50.3, and 78.5. And our points look about like this. Over 2 up 12.6 again. We're just approximating because you're not going to find that value of 78.5 exactly. It's just pretty close to the 80 line there. Okay, 0 would give us 0, so we could also put that. Okay, and the question is this a line? No, it's kind of curving like this. Okay. Actually, let's see here. This point should be a little bit lower. Let's try that again. It's going to go a little lower like that. Okay. All right. So no, this is a curve. Okay. In fact, it's a curve we call a parabola. So this one is non-linear. All right. So we've got two linears, two graphs that make a line, and one that does, and two that don't. Okay. Now notice, let's real quickly take a look at the equations up top here, because the equations kind of are going to be a key here. Okay. We notice that this perimeter is, on this rectangle, is 2 times the length, which is 2x. So let's write that as 2 times 2x. Okay, 2 times 2x plus 2 times the width, which is x. And that's just 4x plus 2x, which is 6x. So really the perimeter here is just 6x. Okay, so the perimeter is really just 6 times x. And if you look at that, that's true. Okay, 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, so on and so forth. Here, we could come up with an equation for the area. Area is length times width, but the length and width are x and 2x, or let's call this the length 2x, and the width is x. And so that's 2x squared. Okay? So our area is 2x squared. So we want to know a couple things. We want to think about how could we know that the graph is going to be linear. 1, by looking at the graph. That should be easy. 2, by looking at the table. And 3, we want to just look at the formula and know. Okay, so let's take a quick glance here. Notice these are going up by the same thing every time. 6, 6, 6, going up by 6 every time. But here we're going up 6, and then 10, and then 14, and then 28. So we're going up by more and more every time. Actually, that's going up by 18, right? Okay. So, but it's not going up by the same thing. It's not a constant change. If we look down here, we're going up now. We round it off, so every time we're going up by the same thing. We can't see it exactly because we're we round it. But here you can see we're definitely not. You know, we're going up about 9.5 there. And this one, if we subtract these two, we're going up by about 16, 15 point, what is that, 7-ish? Okay, it's definitely not 9.5. And we're going up by more and more every time. Okay, so it's not a constant difference. This last one is 28.2. Okay, going up by something different every time. So it looks like if it's linear, then we're going up by the same thing in the table. We're going up by a constant amount. If it's not linear, it's going up by something different every time. Also looking at the equation, this equation is 6 times x, and that gives us a line. This is 2 pi times r. Those were both lines. On our nonlinears, we have 2 times x squared. Here we have pi times r squared. Remember, pi is just a regular old number. Okay, so what's difference there? Well, these two both have squareds in them, x squared or r squared. This has just a plain old something times x and something times r. So let's go next page and put some thoughts down. So on the next page, take a moment and think about this. How do you know the patterns you found represent functions? Think about that. And then how can you determine whether a function is linear or nonlinear? Take just a minute and write down a couple thoughts about that. First of all, to know it's a function, we know that every x has only one y. If we look at the table or the graph, that's true. And the graphs follow obey the vertical line test. So if a graph is linear or a function is linear, the graph is a line, the equation doesn't have exponents, and the table changes at a constant rate. We're adding or subtracting the same thing every time. So those are kind of the key things we just saw. Okay, so a few little vocabulary things here. A linear equation in 2 variables, well, it's a linear equation if we have no exponents and we're just multiplying plain old x to the first power. We just don't write that first power. Doesn't have any exponents or square roots or anything like that. Okay, a linear function is a function whose graph is a line. Okay, something like that. That's the key. When we graph it, it makes a line, and we just saw that we can find it out. We can figure out that it's linear in lots of different ways. It's a nonlinear function. Well, if it doesn't make a line. All other functions are nonlinear. Okay? And the solution to a linear equation in 2 variables, well, the solution is the set. We say it's a set of all points set of all ordered pairs. Okay. Those are the x, y's that make the equation true. All right. There's a whole bunch of points. Okay. So for example, if y equals 6x, there's a whole bunch of points. Okay, there's points like 1, 6, or 2, 12. When x is 2, y is 12. Or 3, 18. When x is 3, y is 18. Okay, and we can go on and on and on. Dot, dot, dot. Okay, so those are the solutions. The solutions are the point, and that's a real foundational thing. The solutions are the points. Now we have a discrete domain if we only use certain numbers, okay, or only use integers usually. Okay, that's discrete. We don't draw the line in for x. Okay, continuous domain is we use all decimals. X could be any decimal for X. All right, all real numbers we say. All right, let's take a look at a couple quick examples. So flipping the page here, we've got an equation y equals x plus 3. And y equals x plus 3 here, x can be lots of things, okay? Here we're describing the function in words. We've got an output that's 3 more than the input, so that's x plus 3. Input is x, output is y. So if we put -1 in here, we get 2. If we put 0 in here, we get 3. If we put 1 in here, we get 4, 2, we get 5, so on and so forth. Okay, so there's it as a table. Okay, and we can see that since the x's are going up at a constant rate, the y's are going up by 1, going up by 1, going up by 1. We could do it as a mapping. -1 goes to 2, 0 goes to 3, 1 goes to 4, 2 goes to 5, so on and so forth. We could plot the points as a graph. This is a continuous graph because you could also put decimals in here, right? It's okay to put 0.5 or 3.1 in there. Okay, so these are all linear functions. Okay, we have a constant change. Okay, going up by 1, going up by 1, going up by 1. We see we have powers of 1, because that's really x to the first and y to the first. We have a line here. Okay, and here we also have the constant change. Ways to see that it is a function. I'm sorry, it's a linear function. Okay, and then back on that discrete domain just means that if these are discrete numbers, 1, 2, 3, 4, 5, there's no line in between, because those are the integers from 1 to 5. That's discrete. It's a set of input values that consist only of certain numbers. A continuous domain is a set of all values, all numbers in an interval. So continuous would mean we draw it like this, because this includes 2.5, 2.6, 2.7, 3.99999. That's continuous. Okay, so there's a quick introduction to linear functions. Now go to the next page there and see if you can identify some linear functions.